Okay, so next type of lifting machine is the screw jack. And as you remember, I started this video with the example of a screw jack only, and I told you how a small screw jack is capable of lifting a big cars or big trucks worth tons of load. Okay, so what actually is the screw jack and how is it working? So we have a screw obviously, and these are the threads of the screw. Okay, we have a lever here and we are applying a force on this lever. So what will happen, this screw will be turned and as a result this will be lifted up, this will advance in axial direction in order to lift the load W. Getting this now? Okay, now suppose the mean radius of this screw is small r and the pitch of the screw is suppose P. Now what actually is the pitch of the screw? The distance between the two threads is nothing but the pitch. The distance between two threads is nothing but the pitch. Okay, there is another term called lead of the screw. These are two different terms. This term lead is often confused with pitch, but both are not the same. What is lead? Lead is the axial advancement of the screw with one rotation, one complete rotation of the screw. That means if I am rotating this by a complete one rotation, 360 degree, how much axial this screw will advance in axial direction, upward or downward, that is nothing but the lead. Okay, now you would say that the same thing is the pitch. Pitch is actually the distance between the two threads, and in case of single headed screw, single headed threads means in which a single thread is wrapped all over the screw. Okay, we also have a double start thread, single start thread and double start thread, what we call as. So in double start thread there are two threads which are wrapped over the screws. In single start thread only single thread is wrapped over the screw. So in case of single start thread, this pitch will be equal to lead. Why? Because in case of single start thread, if I am turning this by one complete rotation, this screw will advance in axial direction by an amount, one pitch, as I told you previously. But if we have a double start thread, then what will happen? Then the total advancement of the screw in axial direction is nothing but 2 times of the pitch, because there are two different threads. Okay, so in case of double start thread, in single start thread, pitch is equal to lead. Okay, and in double start thread, this lead is equal to 2 times of pitch, not just the pitch. Getting this or not? Okay, now this screw jack works on the principle of inclined plane. Okay, if you can see here, we just have the inclined plane and we are raising the weight with the help of this inclined plane only. Okay, so if I draw the free body diagram with this inclined plane, so we have an inclined plane, suppose at an angle theta. Okay, and this theta is actually called the helix angle of the thread. Theta is nothing but helix angle of thread. Okay, so we have this inclined plane which is inclined at an angle theta, which is helix angle, and we have a weight, suppose W, on this particular plane. W weight is acting. Okay, now if I draw the free body diagram, now the weight is acting vertically downward, W weight is acting vertically downward. The normal reaction will act normal to this plane, suppose N. Okay, and if the weight is advancing in upward direction, if we are lifting the weight, okay, so the weight is getting lifted, so friction force will act in opposite direction. Okay, so friction force will act in this direction, in opposite direction. The magnitude will be equal to mu into N. Okay, and the resultant of these two, that means mu into N and N, the resultant of these two is nothing but R. Okay, and the angle which this R makes with normal is nothing but phi, and we know what, tan of phi is equal to mu, which is coefficient of friction. We have already studied all these things in friction unit. Okay, or you can say phi is equal to tan inverse of mu. Getting this or not? Okay. Now apart from this, we are applying a force in horizontal direction. Okay, and if I consider the same force F in this particular radius r, if I consider the same force F at this particular radius r, let's suppose that force be P. Let's suppose this force be P1. Getting this? I have just put a lever here and I am applying a force F so that the force be reduced. Okay, but actually the screw jack is only this much. So if I am applying a force here, suppose that force be P1. Okay, and if I want to determine the value of this P1, this is simple to determine. So this is equal to F into L, total moment about center is equal to F into L, and this should be equal to P1 into R. The moment for both these forces should be equal. That means F into L should be equal to P1 into small r, or you can say from here this P1 will be equal to F into L upon R. Okay, so this is the value of the force if it is applied on the screw jack only. The F is the force which is applied on the lever, P1 is the force which is applied on the screw jack. Getting this? Okay, so we have one force also P1 which is acting in the horizontal direction like this. Getting this not? Oh, sorry. This force P1 is acting in the horizontal direction like this. Getting this not? Okay. Now applying equilibrium equation. Summation of Fx is equal to 0 and summation of Fy is equal to 0. Okay. Now what does summation of Fx is equal to 0 suggest? Now just look at here carefully. This angle is theta. Okay, that means this plane is making an angle theta with horizontal. So the perpendicular plane, which is normal reaction, this will make an angle theta with the vertical. Okay, so this angle will be theta. If this angle is theta, this angle will be theta. Okay, now what is summation of Fx is equal to 0? So in this direction a force P1 is acting, in this direction a force R sine of theta plus phi is acting. Okay, this R will have two components, horizontal and vertical. Vertical component will be equal to R cos of theta plus phi, horizontal component will be equal to R sine of theta plus phi. That means this P1 will be equal to R sine of theta plus phi. Summation of Fx is equal to 0. Okay. Similarly, applying summation of Fy is equal to 0. So we have W weight acting in downward direction and we have a vertical component of this R acting in upward direction. Okay, so from here this W will be equal to R cos of theta plus phi. This is equation number 1, equation number 2. Okay, now dividing these two equations, what we will get is P1 by W is equal to R gets cancelled out and I will get what? Tan of theta plus phi. Okay, or you can say P1 is equal to W tan theta plus phi. Getting this or not? Okay. Now if I want to determine the efficiency of this screw jack, what will be efficiency? As we know that efficiency is nothing but ideal effort applied upon actual effort applied. Ideal effort obviously will be less than that of the actual effort. So efficiency will be equal to ideal effort upon actual effort. What is ideal effort? If the friction, the effort applied, if the friction is not acting. Okay. So if the friction is not acting, then obviously this phi will be equal to 0. Okay. For P ideal, phi will be equal to 0. Why? Because mu is equal to 0. We are assuming that friction is not acting in case of ideal condition. Okay. So this will be equal to what? So this P1 will be equal to, or you can say P1 ideal will be equal to W tan of theta. Okay. And P1 actual, as we know, is equal to W tan of theta plus phi. Okay, so from here we can get the value of efficiency, which is P ideal by P actual. So this W gets cancelled out and we will get what? Tan of theta upon tan of theta plus phi. Getting this or not? Okay, so this is the formula for efficiency of the screw jack. Clear or not? Okay. Now if I want to determine the maximum efficiency, then what I will have to do is to differentiate this efficiency with respect to theta and equate it to 0, because the only variable here is theta. Okay, so just for maximum efficiency, for eta max, for maximum efficiency, d eta by d theta should be equal to 0. Okay, so just differentiate this. So this will be equal to d by d theta of tan theta upon tan of theta plus phi. This should be equal to 0, and from here we will get the value of theta. On solving this, we will get the value of theta as pi by 4 minus phi by 2. This is the value of theta for which we will get maximum efficiency. Okay, if I put the value in the formula for efficiency, I will get the value for maximum efficiency, and this eta max will be equal to 1 minus sine of phi upon 1 plus sine of phi. Okay, so this is the maximum efficiency of a screw jack. Okay, theta I told you is the helix angle. Clear or not? Okay, now what if the weight is getting lowered? For lowering of weight, okay, now what will happen if I draw the free body diagram here? So we have an inclined plane, as we have already discussed. This angle is theta. Okay, the weight acting is vertically downward, normal reaction acting in normal direction n. Okay, and now the weight is getting lowered. So because the weight is getting lowered, obviously the frictional force will be acted in opposite direction. Okay, so this angle is theta, so obviously this angle will be theta, this angle will be theta. Okay, friction force will be acting in opposite direction, so this will be the direction of mu into n. Getting this not? Okay, now what about resultant? So I will get the resultant somewhere around the here. This is resultant, and this angle will be equal to phi. Okay, the angle of n with vertical is theta, and the angle of n with r is phi. Okay, so don't get confused with this. Everything will be same as discussed in the when the load was getting upward. Okay, only difference will be now this r will have two component. One will be vertical, which is r cos of theta minus phi. There it was r cos of theta plus phi. Here it will be r cos of theta minus phi. Theta minus phi. This angle is theta minus phi. Similarly, horizontal component will be equal to r sine of theta minus phi. Okay, obviously the direction of force will be opposite. So the direction here is suppose P2, and the force acting is suppose P2 for lowering the load. Okay, so same result we will get just with opposite sign. So this P2 will be equal to W tan of theta minus phi. Getting this now? Okay, now what if phi is greater than theta? If phi, that means the friction angle is greater than theta. Now what will happen? Phi is greater than theta, that means this term, this P2 will be negative. This means this P2, the direction of this P2 will be same as that of the P1 which we discussed for raising the load. Getting this not? Okay, so obviously this will not be lowered because the direction becomes opposite. So this will not be lowered, or you can call it as the self-locking machine. So this becomes the condition for self-locking. If phi is greater than theta, then we can say that the screw is self-locking. Very important thing. So if you want to check whether the screw is self-locking or not, just check the value of phi and theta. If phi is greater than theta, then the screw is self-locking, and if it is less than theta, then the screw is not a self-locking, it will be a reversible machines. Okay. Next, coming to the velocity ratio. Now what is velocity ratio? Now this I already told you while I was illustrating with the example of car. What will be velocity ratio? Velocity ratio is nothing but the distance travelled by effort to the distance travelled by load. Okay, so what is distance travelled by effort? And the effort we are applying is F. The total distance travelled is nothing but 2 pi L. The radius is L. Okay, so the total distance travelled is nothing but 2 pi L, capital D by small d, or this can be written as 2 pi L. Okay, and while this is covering the distance of 2 pi L, this screw will raise by an amount P considering single headed screw, this screw will raise by an amount p, so this will be equal to 2 pi L upon p. This is nothing but the velocity ratio of this screw jack, 2 pi L by p. Clear or not? Okay. Now what if I want to determine the value of F? We have the value of P1, and if we want to determine the value of F, that means a force which is to be applied on a lever of length L. What will be that force now? So we have already discussed that F into L, this should be equal to P1 into small r. Okay, or you can say F is equal to P1 into small r upon L. So this will be equal to W tan of theta plus phi into r by L. So this much force is required in order to lift the load W on the lever which is of length L. Getting this or not? Okay. Okay, so we will solve some questions now. First question, a simple jack has threads of pitch 5 mm and handle of 45 cm length. Find the velocity ratio if an effort of 100 Newton applied at the end of handle lifts a load of 12,000 Newton. Find the efficiency of jack. Okay, so what is the question saying? We have a simple jack whose pitch is 5 mm, the length of the handle is 45 centimeter, refer that figure. We have to determine the velocity ratio. Okay, so what will be the velocity ratio? This will be equal to 2 pi L by p, as I told you. So this is equal to 2 pi into 45 divided by pitch is 5 mm. In terms of centimeter, this will be equal to 0.5 centimeter. So this is equal to 565.4. This is velocity ratio. First answer. Second, it is asking about the efficiency. Okay, so what will be the efficiency? Efficiency is nothing but mechanical advantage by velocity ratio. Mechanical advantage is load per unit effort upon velocity ratio. Okay, the load given is 12,000 Newton and effort we are applying is 100 Newton by 565.4. This will be equal to 21.22% answer. Okay, so very simple question. We just had to determine the velocity ratio and efficiency. Clear or not? Okay. Another question. So next question. A screw jack having square threads of mean diameter 6.25 centimeter and pitch of 12.5 mm has a mu, a coefficient of friction of 0.05. Find first a tangential force which should be applied at the end of 30 centimeter long handle to raise a load of 5000 Newton. Second, is it self-locking? If not, find the torque required to keep the load from descending. Okay, so we have a screw jack. What are the given figures? The mean diameter small d is given as 6.25 centimeter. The pitch is given as 12.5 mm. Coefficient of friction mu is given as 0.05. We have to determine the tangential force. That means we have to determine F applied at the end of 30 centimeter long handle. That means the length of the lever L is given as 30 centimeter to raise a load of 5000 Newton. That means the load W is given as 5000 Newton. Clear or not? Okay, so we have to determine the total force which is to be applied at 30 centimeter long handle in order to lift the load of 5000 Newton. Okay, so we have already determined the value of P1 in order to lift this load. This P1 is equal to what? W tan of theta plus phi. Okay, now first thing is to determine the value of theta. Now how can we determine the value of this theta? Okay, so now we considered this inclined plane. This was our inclined plane. Okay, for one complete rotation we just consider the thread of one complete rotation, and with one complete rotation the vertical advancement of the screw is P, which is equal to pitch. Okay, and this total length is nothing but the circumference. So this is nothing but 2 pi r, or you can say pi into d. This angle is theta. Getting this or not? Okay, so from here I can determine the value of theta. So how can we determine the value of this theta? So tan of theta will be equal to what? Tan of theta is equal to perpendicular upon base P upon pi into D. Okay, so just put the value. P is 12.5 in mm by pi into D in mm will be equal to 62.5 mm, 6.25 centimeter, 62.5 mm. Okay, so from here you can get the value of theta, and this theta from here will be equal to 3.64 degree. First thing. Second, we have to determine the value of phi. This phi also we can determine. How? We have the value of mu, and as I told you, this phi is equal to tan inverse of mu. Okay, or you can say phi is equal to tan inverse of mu is given as 0.05. Okay, so from here this phi will be equal to 2.86 degree. Okay, so now you have the value of theta, you have the value of phi, and you have the value of w. So you can determine the value of P1. So this P1 will be equal to 5000 tan of theta plus phi, 3.64 plus 2.86. So from here this P1 will be equal to 569.8 Newton. Getting this? First thing. Okay, but we don't have to determine P1, we have to determine the value of this F. So how can we determine this, the value of this F? So this F into L is equal to P1 into R, or you can say D by 2. So from here F is equal to P1 D upon 2L. So just put the values. So this will be equal to 569.8 into diameter is given as 6.25 centimeter, and length is also given in centimeters, so no need for conversion. So this will be equal to 6.25 divided by 2 into 30. So from here this force is equal to 59.34 Newton. Okay, so this much amount of force is required to be applied at the end of 30 centimeter long lever or handle. Getting this or not? Okay. Now what does the second part is saying? Now second part is asking whether if it is a self-locking device or not. First thing, and if it is not a self-locking device, then we have to determine the torque required to keep the load from descending. Okay. So first thing is to check whether it is a self-locking or not. So how can we check? As I told you, just check the value of theta and phi, and in this case, since theta is less than phi, since phi is less than theta, and what was the condition of self-locking? Phi should be greater than theta, and here since phi is less than theta, so this is not a self-locking device. Okay, since phi is less than theta, so this is not a self-locking device. Okay, so if this is not a self-locking device, then we have to determine the torque, minimum torque required in order to not let this screw go downward. That minimum torque we have to determine. That means in order to prevent this from descending. Clear or not? Okay, so how much force actually is applied while descending of this screw? P2 force, as I told you, and that P2 is nothing but W tan of theta minus phi. This much amount of force was actually required, to descend this screw. Okay, so from here we can get the value of this P2. So this P2 from here will be equal to, W is given as 5000 Newton, 5000 into tan of theta minus phi, theta is 3.64 minus 2.86. Okay, so from here we can get the value of this P2. Okay, so this P2 is actually the force applied in opposite direction in order to descend this load. Okay, and if we want to prevent that descending, we will have to apply a force in forward direction again in the direction of P1. So we want to determine that minimum amount of force that is required in order to prevent this screw from descending. Getting this or not? Okay, so whatever torque this P2 force is applying, minimum at least that much torque we should apply in forward direction in order to prevent it from descending. Okay, so how much torque this P2 is applying? This P2 is applying a torque of So the minimum amount of torque, you can say T will be equal to this P2 into the distance d by 2, P2 into the distance d by 2. Getting this or not? Okay, so just put the value. So this will be equal to 5000 10 of 3.64 minus 2.86 into d by 2, which is equal to 6.25 by 2 into 10 raised power minus 2 in terms of Newton meter. So from here this will be 2.12 Newton meter. Okay, so this is actually the torque which is applied while moving downward. So if we are applying this much torque in forward direction, obviously this will not move, this will the screw will not lower, it will stay in its original position. We are not raising the screw further, we just have to prevent it from lowering. So what we did was we determined the force which is required, or the force which is being applied while lowering. So this much amount of force is applied, this much amount of torque was getting produced. So at least this much forward torque we should apply in order to prevent this from lowering. Getting this one? Okay. Okay, so we have this next type of lifting machine which is wheel and axle. Okay, so what is this wheel and axle? So we have this arrangement, we have a wheel and an axle, and the threads are wrapped on this wheel and axle. Okay, how the threads are wrapped? Such that if the thread in this axle is getting wounded, then the thread in wheel will get unwound. That means if I am unwounding this thread will be wounded. You can see the direction of these threads. The direction of this wheel and axle will be same, but if this is getting unwounded, this will be wounded, and vice versa. If this is getting unwounded, this will be wounded. So what I am doing is, the diameter of axle is less, the diameter of wheel is more. I have to lift this weight W up, and I am applying a load P on this, on the thread of the end, at the end of the thread of the wheel A. Okay, so one end of this thread is attached to the effort, and another end is attached to this axle of this thread. Similarly, one end of this thread is attached to the load which is to be lifted, and other end is attached to this wheel. So this is the whole arrangement. Okay, now what you will ask, now what is special about this arrangement? I will tell you. Okay, so what is the velocity ratio of this particular arrangement? What will be the velocity ratio? What is velocity ratio? That is distance travelled by effort to distance travelled by load. Okay, now for one complete revolution of wheel and axle, this effort will move by a distance equal to the circumference of this thread wrapped on this wheel. I think this, for one complete revolution, the distance travelled by this P will be equal to pi into capital D. For one complete revolution, this much thread will be unwounded, and as this much thread will be unwounded, this thread will be wounded up, and this weight will be raised. Okay, now how much this weight will be raised? This weight will be raised equal to the circumference, the circumference of this thread on this axle. So this will be equal to pi into small d. Getting this now? Okay, so this velocity ratio will be equal to what? Pi into capital D upon pi into small d, or you can say capital D by small d, where capital D is the diameter of wheel of bigger diameter, and small d is the diameter of axle, smaller diameter. Getting this not? And as we know that capital D is greater than small d, therefore this velocity ratio obviously is greater than 1. Okay, and if it is an ideal machine, then obviously this mechanical advantage will be equal to velocity ratio, since efficiency is equal to 1, and this will be equal to capital D by small d, which is greater than 1. This means less effort will be required in order to lift more load. Okay, and this you have already seen in your laboratory, in your engineering mechanics lab. I will show you the video also, you can see here. So if I am applying a load, if the load is applied on the thread on the wheel, okay, you can see that the string on the wheel will be unwounded, and the string on the axle will be wounded, raising the weight. Getting this not? Okay, I think you have recalled what you have done in the engineering mechanics lab. Okay, so this is nothing but the wheel and axle arrangement. Okay, next is the differential wheel and axle. Okay, so this velocity ratio will be equal to distance travelled by effort to the distance travelled by load. Okay, so how much is the distance travelled by effort? That is pi into d. What is distance travelled by a load? This is equal to pi into d2 minus d1 by 2. This pi gets cancelled out, so this will be equal to 2d upon d2 minus d1. So this is the velocity ratio for this differential wheel axle. Getting is not? Okay, so these were few simple machines, simple lifting machines. You can see few more simple machines from your book. There are few more machines like worm and worm wheel, like winch, crab, differential pulley block, but those the questions are not much raised from those parts, so we are leaving this. If you want, you can refer it from the book. Okay, so this completes this unit of simple lifting machines. Thank you.